Welcome to Textbook Engineering Problem, where we explore complex engineering problems and discuss different methods for solving them. In this video, I'll be breaking down a problem and discussing different ways to tackle it. However, keep in mind that there is no one correct path for some of these solutions, and I encourage you to share your own insights and thoughts in the comments. Together, we can learn and improve our problem-solving skills. So, sit back, grab a notebook, and let's dive into today's problem. I'm going a little bit out of order because I got a request from somebody in one of my previous videos to take a look at problem number 4.6. So I'll be taking a look at problem number 4.6 from Elementary Principles of Chemical Processes, 3rd edition. And we'll take a look at this problem and see what we can do to figure out the different methods of tackling this. Okay, so in this problem, it says a distillation column is a process unit in which a feed mixture is separated by multiple partial vaporizations and condensations to form two or more product streams. The overhead product stream is rich in the most volatile components of the feed mixture, the ones that vaporize most readily, and the bottom product stream is rich in the least volatile components. The following chart shows a distillation column with 2 feed streams and 3 product streams. Okay, so we've got our picture here that shows the 2 streams going in, the information that we know about the 2 streams, and then the streams going out and the information that we know about these 2 streams. The one thing that I saw that was a little bit confusing that you might miss when you're looking at this problem is that at the top here, the units of the mass flow rate of stream 3 are in kilograms of A per hour. And so that means that only the most volatile compound is coming out at the top, and the other amounts of elements, B and C, are not present in the top stream, or at least they're negligible. The amount that's in them is negligible. And so you just take them to be 0. And I assume this simplifies the problem somewhat. So we have a pure stream A coming out at the top. How many independent material balances may be written for this system? Okay, so we have 3 different independent material balances that we can do because we have 3 different elements. We have material A, material B, and material C. And so we can do 3 independent mass balances around the 3 different materials that we have in this reactor. So that's it for part A. How many of the unknown flow rates and/or mole fractions must be specified before the others may be calculated? See example 4.3-4. Also, remember what you know about the component mole fractions of a mixture. For example, the relationship between x2 and y2. Briefly explain your answer. Okay, so in part B, they're asking us to basically do a degrees of freedom analysis. Okay, so what they're asking is how many of the unknown flow rates and/or mole fractions must be specified before the others may be calculated. So let's look at degrees of freedom is equal to the number of unknowns minus the number of independent equations. So let's look at how many unknowns we have. 1, 2, 3, 4, 5, 6, 7 unknowns in this problem. So we have 7 unknowns. And how many independent equations do we have? Well, we have 3 mass balance equations that we can do that are independent. And then we have another balance that we can do here where WA plus WB, WA plus WB has to equal 1. The same thing here. WA plus WB plus WC has to equal 1. Okay, so I think that's it. I think we can only get, there's only 5 independent equations that we can write. So there are 5 independent equations. So that means that the degrees of freedom is 2. So we have 2 degrees of freedom in this problem. Okay, which means that the problem is not fully specified. So we can't calculate what goes into this, what goes in and goes out of this reactor without fully, or without assigning a certain number to other parts of this reactor. Or at least reducing, I guess what I mean by that is we can't calculate all of the unknowns in this process unless we reduce the number of unknowns. So if we reduce the number of unknowns so the degrees of freedom is 0, then we could specify all of the unknowns with the given information that we have. For more information on that, go ahead and read 4.3D. It's the degrees of freedom analysis section of your book. It goes over it in a lot more detail. But feel free to also ask questions and in the comments, and I'll see what I can see if I can explain anything that's still unclear from that. Okay, so for part C, it says, suppose values are given for M1 and X2. Give a series of equations, each involving only a single unknown for the remaining variables. Circle the variable for which you would solve. Once a variable has been calculated in one of these equations, it may appear in subsequent equations without being counted as unknown. Okay, that's great. So we just have to do kind of a symbolic solve of this problem, where we can solve for the different variables, assuming that we have a reduced number of unknowns. So there won't be a numerical solution to this problem, but we can show that we can solve for our other unknowns given the 5 constraints that we have on this system. So we counted 5 constraints. We have 3 material balances that we can do, and then we have 2 physical constraints that we have on these 2 streams where the mass fractions have to add up to 1. Okay, so let's use our 5 different equations and see if we can solve for the remaining unknowns that we have. The remaining unknowns are Y2, M3, Y4, Z4, and MS. And everything else is known. Okay, so let's start off with our material balances here. So let's do A. Okay, so what A is going in? The only in for A is stream 2. So M2 times WA 2 equals, we've got the only spot where A comes out is stream 3 and stream 4. So let's do stream 3 and stream 4. Stream 3 and stream 4. Okay, x2 is known, so m2 is known. This becomes x2. We'll substitute that in because we know x2. M3, we don't know m3, so m3 is an unknown. WA3 is equal to 1, so WA3 becomes 1, so 1 times anything is equal to itself, so we'll just leave that out. That goes to 1, plus M4 is known, so we'll just leave that, M4, plus WA4, that is also known. So we'll just leave that as that. Okay, so the only unknown in this problem, in this balance, is M3. So we know what M3 is, okay? Now let's do B. Where do we have B going in? We have B going in stream 1 and stream 2. So and then we have B going out in stream 4 and 5. Okay, so let's look at our unknowns. In this equation, we've got WB2 is an unknown. M3 does not appear here. WB4 and M5. M5. Okay, so we have 3 unknowns here, but let's do one of our physical constraints. Physical constraint number 1 is that these mass fractions need to sum to equal to 1. Okay, so WA2 plus WB2 has to equal 1. And that means that WB2 equals 1 minus WA2, and all those are known. So that means we have WB2 in terms of things that are known. So now WB2 is known, so that means in part. So now we know that this WB2 is no longer an unknown because we have it figured out right here, defined. Just like anytime M3 shows up, we'll know that that's also defined. Okay, so let's now do our part C. C goes in stream 1 and comes out 4 and 5. So 1, 4, and 5. So WC1 mass 1 equals mass 4 WC4 plus mass 5 WC5. Okay, so let's look at all of our unknowns here. We've got WC4 and mass stream of 5. So WC4 and mass flow rate of 5. Those are the only unknowns in this one. So we only have 2 unknowns here. And then we've got one more physical constraint, and that is that the sum of the mass fractions in part C, the sum of the mass fractions in stream 4 need to sum to 1. Okay, so that's WA4 plus WB4 plus WC4 has to equal to 1. Okay, and we've got two unknowns here because we know how much A is in that stream. Okay, so now we can, we've got three equations and three unknowns here. So now we can just probably solve these by substitution. It'll get probably super messy from the looks of it because I don't think we may be able to eliminate some variables, but it looks like it's going to get pretty messy. So let's hey, this is me from the future. I am in editing here. I know that at this point in the problem, I started looking into how long this would take. The problem is basically solved at this point. It's just a matter of like doing a bunch of algebra, and it takes a long time. So I think for the rest of this video, I'm just gonna speed up all of these steps, and you can try and follow along, or you can pause the video wherever you want, but for the most part, we're just going to tackle this brute force by substitution and variable elimination through subtraction and addition of the three different equations that we have. At the end, we end up with an equation for each of the five unknowns, so I try to highlight those as I'm going through, but I think at this point I'll just kind of cut out the sound until the end and fast forward through so you guys can just keep track of the algebra on your own. I use different variables, WB, weight fraction variables instead of the variables that they gave to us, but at the end I substitute in their variables. So keep your eye open for that as well if you're working in the variables that they gave to you. All right, I'll see you at the end of the episode here. Okay, so that took a long time. It's a lot of algebra and substitution and cancellations and things like that, but that would be how you solve it. So if you take m1 and x2 to be known variables, and you put all of the unknown variables such as y4, z4, m3, x2, and m5 all in terms of either x1 or m1, x2, or a combination of both, then you can solve for each one of these variables, and that is because the degrees of freedom are at 0. The equation is totally satisfied if you only have 5 unknowns and you have 5 independent equations. So hopefully that helps. It was pretty long. There's a lot of algebra, so it's just a lot of shuffling around. So I didn't do a lot of talking for a lot of it. So I just skipped ahead so that you could kind of see how to put those solutions together. But the main part is just the beginning part. So hopefully that was helpful. Again, thanks for reaching out and asking for help. And hopefully you can see how these things are put together, these problems are put together, and please leave a comment, and in the future, others, if you need help, and I'd be happy to walk through a problem with you, and be sure to ask the questions you need and get the help you need. Thanks for watching, and I hope you found this video helpful in your problem-solving journey. Remember, there are other routes you can take to arrive at the same correct answer, and I encourage you to leave a comment with any additional insights or questions you may have. Also, if you have any specific engineering problems you would like me to cover, please let me know in the comments. Your feedback is valuable, and I look forward to continuing the conversation with you. Don't forget to like and subscribe for more engineering problem videos. Thanks again, and I'll see you in the next video.